Good morning. I hope you are doing well. I'm doing fairly well. This week, I was definitely probably the most frustrated I've been with this project in quite some time. I think like Tuesday, Wednesday, I spent a lot of time just sitting here with my fingers crossed, just staring at the wall, not loving life. But, that's how it goes. Thankfully, I've channeled that energy and put to the side temporarily the things that I was getting frustrated with, and have instead I decided to do some more productive things and do some documentation and some other work that is well needed, and I'm sure that you will all appreciate it. Hello, Batboy. It's good to see you. Yeah. So, despite my frustrations and everything, I'm very keen to show you what I've been up to. There are the thing that I was most frustrated with is also something that I'm kind of like in a way very proud of. We'll get there when we get there. Yeah, it's been a long couple of weeks. Yep, but we got here. Also, by the way, I just want to preface this by saying I'm a little bit sick right now, so I'm a little bit, I don't know, not fully in my right mind. Yeah, so please grant me a bit more clemency than usual. Yeah, seems to be going around in Melbourne. Yep, it's the season for sickness. And I did not update my subtitle, so you'll have to forgive me. Alright, cool. So the first thing, which is really something that I should have done a long time ago, is to simulate what the throws will actually look like from Ball Butler to Jugglebot. So for some, as a reminder of what we're doing here, we've got Ball Butler up on the shelf up here, and that will be throwing down to Jugglebot down here. And I really should have done this a while ago to actually just simulate what that like flight profile will actually look like, and to just to get an idea of what angles are acceptable, what velocities I will need to throw the ball with, well, that Ball Butler will need to throw the ball with, and just to get an idea of what the ball's actually going to be doing. So from this CAD model, I took very rough measurements of where Jugglebot wants to be and where Ball Butler wants to be, and I have made this code here, and there's a link in the description for this code if you want to check it out yourself. And code itself doesn't really matter too much, but the cool thing is these plots. And I love this plot. I spent a little while doing this, and it was a very interesting back and forth between me and ChatGPT, because this stuff is this is projectile motion. Everyone learns this in physics in year 10, so I definitely know how to do this. But my very first inclination when I went to make this plot, I was like, okay, cool, open up ChatGPT, start typing, please make me a plot to generate projectile motion lines. And as I was typing, I'm like, I know how to do this. I should be doing this myself. And I did. I did not use ChatGPT itself for this. I have Copilot on VS Code, so Copilot definitely assisted with a lot of this. But I tried to do a bit of it myself. But the gist here is that we have a throw position, in this case 0, 0, where we have Ball Butler up on the shelf. I'm just calling this the origin of Ball Butler. This is all obviously also in just 2D, because as far as the ball is concerned, its flight is always going to just be 2D. It can't actually move in 3D once it's been thrown. So this is kind of like a plane looking through I guess this kind of perspective. Yeah, and so what I'm doing here is I'm simulating throwing from this position down to Jugglebot. I tried this. I'll talk about the problems with this code in a sec. It does work perfectly fine for what I wanted to do, but there are a couple of edge cases where it breaks. But that's another thing. Yeah, so we're simulating throwing from 0, 0 down to Jugglebot, and these coordinates are pretty proportional to where it actually is sitting in this code. And we're basically we're starting off at 1 degree inclination for Ball Butler for the pitch axis, and then we're sweeping through all of the angles up to 80 degrees. And I believe this simulation has 500 lines in it, and the colors of the lines is just keyed to the angle of the arm. So that's the only thing that's being represented by the color. I do have some thoughts about other ways to represent this, but I think that this just works the best, especially because I have this table off to the side showing some of the data here. So maybe if I move this above me, you might see it a bit better. Yeah, so basically, on the side here, you can see the launch angle. We have the launch velocity, so how fast we need to throw the ball at. the acceleration that is required for the hand to be able to make the ball reach that speed using the parameters of like how long the hand stroke actually is, how much power we need to throw the ball given the mass of the ball and that same hand stroke. And then we also have after the M dash, we've got the landing angle and the landing velocity. These things will come into play a little bit later in the stream as well. So just kind of like keep these rough numbers in mind. Like I find this very interesting. Actually, maybe before I get to what I find most interesting is to think about what the optimum throw might be. And like there's a couple different ways to quantify what optimum might mean in any given context, and even in this one. But for my thinking, by my reckoning, a very immediately obvious way to quantify what optimum might mean is the lowest necessary launch velocity. And that is what this black line is. Well, it's supposed to be black, but because there's so many other lines there, they draw over it. I probably should have changed the way that this is being plotted so that the optimum line is being plotted last, so it's the most obvious, but I didn't, so it just gets kind of like overwritten by all the other lines going over it. And in this case, with these positions, the optimum angle to launch at is 18.1 degrees, and that will give us the lowest launch velocity. And we can actually see, I've got another plot here that we can turn on that shows the launch velocities and the landing velocities. So this black vertical line is like the optimum angle that we saw just before. And the solid lines are the launch velocities. So we have red is in the x-axis, in the x direction, green is in the y direction, and the blue one is like the total launch velocity. And then the dashed lines are for when it lands. So we can see that as the angle increases going along the x-axis, we go from needing no launch, like no y velocity, which makes sense because we're only throwing perfectly horizontally, and we have entirely x direction velocity because that's the only input that we can give to the ball to get it to actually reach where it needs to get to. And then as that launch angle increases and increases, we see the x velocity goes down a little bit, but the y velocity just shoots up. It really rockets up because as we throw higher and higher, we need to throw higher and higher to get the ball to actually like go up and the whole way down to make sure that it reaches where it needs to get to. And yeah, so we can see that the landing velocity is obviously quite a bit higher than the launch velocity because it's so much lower, and we've got that extra velocity from just like the potential energy being lost as the ball goes down. And of course, the reason why there is no red dashed line is because I'm assuming that there's no air resistance here, because realistically there's not going to be in this situation. So the landing horizontal velocity is identical to the launch horizontal velocity. So like the two red lines are on top of each other. Yeah. And as I said, there's a link in the description for the code for this if you want to check it out in any more detail. One good way to verify that this is working is we can run it with the throw being horizontal, like being starting and landing at the same height. And we can see our expectation, because if you've done this projectile motion stuff, your expectation would probably be that 45 degrees is like the most optimum launch angle. And we see, in fact, that it is. If we're starting and landing at the same altitude, then 45 degrees gives us the best launch velocity. Well, the best launch profile, meaning that we need to accelerate the ball the least amount. Yep. And yeah, if we have a low launch angle, then we need a shitload of acceleration to get the ball to get to where it needs to be, because it's just being like zipped across really fast. Yeah. Yeah, cool. So I quite like the simulation. I'm a big fan of it. Where it breaks is if the landing position is above the launch position. I've got some weird business with like negatives in here, and it all just kind of falls apart. So I need to, I don't know if I actually will improve this, because this situation is not really that relevant for me right now. But yeah, just so you're aware, if you plan on using this for situations where the catch position is above the launch position, you're going to need to fix whatever bug is causing this. Yep. But it does work if the catch position is below the launch position, which is what I'm doing. So for my purposes, it's fine. And I was meant to go to the next thing here to let's see, but we already saw it. Yeah. So realistically, yeah, my big hope part of the reason why I did this simulation, let me just pull it up again. One thing that I was curious about, there were a couple things that I was curious about. One of the big ones was I wanted to get an idea of how the landing angle changed as a function of the launch angle. Because here we're sweeping through a launch angle of effectively 0 degrees. It's actually 1 so that it doesn't have divide by 0 problems in certain situations. Which is a janky way to solve it, I know, but it works. We're basically sweeping through a very, very low launch angle up to 80 degrees. So that's a huge range in how much the launch angle is varying by. But we don't want to have such a large range in the catching angle, in like where the ball is landing, because Jugglebot can't span such a large range. Jugglebot can't go so that the hand is like horizontal. Something on the Stewart platform will break if we try to get it to do that. So we only have a much more limited range of how far Jugglebot can actually rotate. So I wanted to get an idea of how that catch angle varied as the launch angle varied. And I find this quite interesting, that the catch angle, this like theta f, the whatever that is, 1, 2, 3, 4, the fifth column here. Yeah, the fifth column varies a lot less. So when the launch angle is 0 degrees, the catch angle is 70 degrees, given the geometry here of the two positions. But when the launch angle is 80 degrees, or 76, the catch angle is only 81. So the launch angle varies by, 75 degrees, but the catch angle only varies by 10, which is pretty good for me. I'm quite happy with this. This means that once Ball Butler launches the ball, if Jugglebot will need to vary its orientation at all to make it like perfectly parallel to the ball coming in, or perfectly like tangential to the ball coming in, it will only need to vary by a very small amount to compensate for whatever error there might be there. So I'm quite happy with this. I wasn't really expecting that. I mean, it kind of makes sense. Like if you see the plot drawn out this way, like it makes sense that those lines kind of converge and there's not much of an angle difference between them. But I don't know if I would have expected that from the beginning. I was kind of surprised to see that. Yeah. So I'm happy with that result. That bodes well, in my opinion, for the future. Cool. And yes, as I said, this is probably something that I should have done a while ago to get an idea of what velocities we might actually need. And also, for full transparency, this is not the order that I did things in the last 2 weeks. 3 weeks. This stuff I only just did in the last couple of days, and I only did it in the last couple of days because of the problems that I've been having that I'll mention at the end of the stream, or later on in the stream. Yes, which I don't want to think about right now. We'll get there when we get there. Cool. All right. So one other thing that I have been channeling my frustration energy into. Before I get this, Batboy asks, have you considered if any of the throws would hit your ceiling? Yes, I have been keeping that in mind, definitely. And I actually don't have the ceiling in the CAD here. Maybe I should include it in like the room simulation. But yeah, there's not a whole lot of room up above. So like Ball Butler will be up on that shelf here. And there's maybe, I've measured it at some point. I think it's like 1.20 meters from the top of the shelf to the roof. So Ball Butler's got like a bit of height in and of itself. So realistically, we've got like 1 meter of height to make this throw. And if you had a look at if you remember the result of the simulation, let's get rid of this one. Many of these throws do go above 1 meter. And it's, I will definitely include in Ball Butler's like brain, in its thinking process, I will absolutely include that hard limit to say, hey, whatever you think the optimum throw is, it cannot be having the ball go more than like 80 centimeters above the launch position, because otherwise it'll hit the roof. Yeah, so it is definitely in my mind, but I don't think it's going to be an issue, especially because like in this case, the optimum throw in terms of the launch velocity, which I'm kind of skeptical as to whether Ball Butler will be able to do this, because that is an extremely low launch angle, but we'll see how we go. But yeah, in any event, there's a lot of like the further we throw up, the less optimum the throw becomes. So I think that this will kind of like I don't think the Ball Butler will really ever want to throw the ball up into the roof, hopefully. So I don't think that will be a problem, but it's definitely on my mind. Yeah. That's a good question. Yes. Okay. So something else that someone was suggesting is that it's worth having a good think about how I'm going to be sending commands, sending information between Jugglebot and Ball Butler, and even just to Ball Butler in general. And for full context here, Ball Butler, as it is right now, will almost always be just throwing balls down to Jugglebot. It'll just be up on the shelf up there, and it'll be throwing to Jugglebot. And that's pretty much it. However, I don't want to set things up with only that use case in mind, because, as you may remember, my long-term goal for Ball Butler is not to be a butler for Jugglebot, it's to be a butler for me. And we need it to be kind of like a self-sustaining system, a self-contained system is a better word. And yeah, so I'm just keeping that in mind, that it has to be able to do all of its own processing with everything, and it has to be able to think for itself, so to speak. So, but at the same time, it needs to be able to communicate with Jugglebot, so the Jugglebot can say, hey, I need a ball now, send it to me now. In much the same way that I will be doing the same thing, either verbally or gesturally. I'll say this symbol means throw a ball, and then it will have cameras and see that I've done that and go, okay, cool. Harrison wants a ball now, I'll send the ball now. So yeah, Jugglebot needs to be able to send commands to Ball Butler in the same way that, in a similar way that I, abstractly, in a similar way that I will need to send commands to Ball Butler. And yeah, someone was suggesting that it's worth having a good think about how this might actually work before I just kind of jump into it and just figure it out on the fly. And I agree that that's a good, it's a good thing to have planned for. And I feel pretty good about my setup, which I'll walk you through now. Fluzzy says, is having Jugglebot be able to pass with other bots something you ever thought about? Subconsciously, definitely yes. And subconsciously, definitely yes. I actually had a dream 2 days ago. And in my dream, in this dream, I so vividly remember seeing Jugglebot and Ball Butler tossing back and forth between each other. And it looks good. I got to tell you that. It's a good looking system. So you just have to take my word for that for now. But yeah, definitely. And it is tricky though, because Ball Butler can't move sideways, and that really limits the number of the types of throws that you can make. You can't have more than one ball being passed between, depending on how you do it, it's very hard to fit multiple balls between two robots where one of them can't move, or two hands where one of them can't move. You can do a half shower. Let me get the balls. You can probably do this sort of thing where one ball's going over the top and the other one's going under. I think that sort of thing can work, but you definitely can't do a normal cascade, because the balls will just hit each other. They need to be able to move side to side for that to work. However, one thing that I've been thinking quite a lot about is having 2 Jugglebots and 1 Ball Butler, because that will allow the balls to kind of cycle through, and the Ball Butler can catch a ball on this angle and then angle over and then shoot it out to the other Jugglebot. And that could allow for some very interesting things. But yes, suffice to say, yes, I have thought about this a bit. Yeah. But it'll be tricky, because the throws will have to be, because Ball Butler can't move side to side, the throws to Ball Butler will have to be extremely precise. So, and we are yet to see how well that sort of thing will work. I mean, Jugglebot can throw quite precisely most of the time. It can get into the catching cone that I showed however long that was ago. But yeah, it'll need a very, very high level of precision for this to work. But yes, this is on my mind. Yep. All right. So yes, how will Ball Butler and Jugglebot communicate with each other? Well, the main information that we need to send to Ball Butler is where we want the ball to land. Where and when do we want the ball to land? In the extreme case, we will have Jugglebot juggling, and it will say it's doing 2 balls in one hand, and then we want to bump up to 3 balls in one hand. We need that third ball to land in a very specific spot at a very specific time, otherwise it's going to mess up the currently existing pattern. So we need this information very precisely, and we need to be able to meet that goal very precisely. Yes. So, yeah. Also, So Ball Butler will need to know where the ball will need to land in terms of X, Y, Z and time, but it cannot be commanded to have the ball have a specific landing velocity, because the landing velocity is more a function of the geometry of how far apart these things are. Like if we, I'm just going to leave this plot open, I think. I'm going to be referring to this a bit. If we have a look at this plot, the velocities here, like, I don't know, just keep these numbers in mind, and I'll run this again with, I don't know, what should we do? Like, let's make the X distance 2.1 instead of 1.1. And I don't know, if you can flick back and forth between the two timestamps of these two images, but you can see that the velocities do change a decent amount. And like as those positions change, the landing velocity and the landing angle will change for the same angle throw. So unless Jugglebot, so essentially Jugglebot cannot command a specific landing velocity to Ball Butler. That's like geometry. That's like nothing can decide that except for just the geometry of the situation, which means, and Jugglebot will also need to know the angle that the ball is coming in at, but if we know the landing velocity, then we know the landing angle, because we can just get the components of the velocity and figure out the angle from that. So this means that if Jugglebot knows where Ball Butler is, then Jugglebot on its computer, on the Jetson, can calculate the landing velocity of the ball, and it can do all of this internally by itself. However, and this would mean that we don't need to send anything from Ball Butler to Jugglebot. So Jugglebot will say, hey, throw me a ball to XYZ at this specific time, and we can just assume that will happen. Maybe there can be like an acknowledgement signal or something, but then that will just happen, and Jugglebot will just be ready, expecting the ball to land at the time that it commanded, and at the position that it commanded to. And it will already know what angle it needs to be at, because it knows where Ball Butler is, and it can figure all of that out itself. However, this requires doing the Ball Butler inverse kinematics on the Jugglebot computer, which means we need to store the Ball Butler geometry on the Jugglebot computer, which is not really ideal, because if we're running those inverse kinematics calculations on the Ball Butler computer, and we're also running on the Jugglebot computer, that means we have like two copies of this thing running at the same time, and that requires me to keep both of those current. Like if I ever change anything about the geometry of Ball Butler, and I update it on the Ball Butler computer, but I forget to update it on the Jugglebot computer, it's not going to work. They're not going to be in agreement about what Ball Butler looks like, and so they won't agree on what type of throws Ball Butler will be making. So this is kind of messy, and I don't love it. And it will also mean redoing the calculations that are already being done on the Ball Butler teensy. So it's just kind of like, it's like the opposite. It's like the flip side of redundancy. It's like the negative side of having redundancy. Yeah, so it's not good. Otherwise, instead of having Jugglebot know Ball Butler's position, which it can do, because I've got these motion capture cameras, and I'll be using those cameras so that the system in general knows where Ball Butler is. Like, these things will have access to Ball Butler's position. However, I don't love this workflow of having Jugglebot use that information for any of the calculations or anything. So if we don't have Jugglebot doing those calculations, instead, Ball Butler will need to tell Jugglebot, hey, you told me to throw a ball to XYZ at this specific time. I'm going to do that, and the ball will be coming in with this velocity. And from that, you can figure out the angle, like these three velocity components. The other option, which I thought of a little bit later, is to so that we don't have like this redundancy, I don't know what the better word is for that. I definitely know it, but I can't think of it right now. Instead of having that like duplication of effort, we could do all of the inverse kinematics and all of this calculation stuff on the Jugglebot computer, and the Jugglebot computer will just say, hey, make your three axes, make your yaw at this angle, make your pitch at this angle, and then throw at this speed. And that's it. So we'll basically be giving the the low level commands to Ball Butler, and Ball Butler will just say, yes, sir, I'll just do that. But I don't love this plan. Oh, I'm covering up the words. Oh, I forgot my numbers. Yeah, I don't love this plan because this means that it will be less useful for when I am... like it's not planning for the eventuality where I am interacting with Ball Butler. Like if I have Ball Butler in the park, I can't do these calculations myself and say, hey, you're at this angle, pitch at this angle, and then throw at this speed. That's not going to happen. I can't run that math. That's not how my brain at least works. Yeah, so it would definitely work for this purpose, and like it is definitely going to be quite some time before Ball Butler is actually with me in any kind of reasonable capacity. But it seems like it's worth trending in that direction now if the options are relatively equivalent. Which I honestly see all three of these options. I mean, the first one's kind of crap, but I see like these last two options as being like both valid and they would both work. It's just a matter of which one I want to pick. One other downside of doing the calculations on the Jetson is that the Jetson's already doing a lot of stuff for Jugglebot, and I don't love the idea of just giving it more work to do because, I don't know, it is a very powerful computer and I have no real reason to believe that I'm like hitting any computational limits on it, but it's like, why give it more to do when like the Ball Butler has this very powerful teensy on it that can definitely do this stuff. So I don't know, it feels like distributing it is a sensible way to go. Craig, having the X and Y scale so different on those plots makes the angles unintuitive. That is a very fair point. Yes. Yep. Apologies. Yep. That boy says, this sounds kind of like a problem that you could solve with ROS. I have an idea. Interesting. I've got something to say about ROS, but I'll get there in a bit. But I'm interested in your idea. Yes, and as I said, I'm not a fan of this last idea. So I am operating, if it wasn't clear already, my favorite option is to have Ball Butler telling Jugglebot what the landing velocity will be. So Jugglebot will say, hey, I want a ball to be at XYZ at this specific time. And Ball Butler will say, yes, sir, here is the velocity that the ball is going to come in with. So the next question is, given that we want to work within this kind of like schema, how should we actually send these messages between the two systems? First up, we can have a look at Jugglebot to Ball Butler. And so what we need to send is XYZ and time of when the ball will be landing. And ideally, this would fit inside a single CAN frame because these systems are connected over a CAN bus, and you'll see soon what that actually looks like, schematically at least. Bit of a spoiler. And yeah, so ideally this will fit inside a single CAN frame, which is 8 bytes. And as a reminder, 1 byte is 8 bits, which is helpful for calculating how we want to structure this. Yeah, so the first question is, how many bytes do we need to encode the position information for all of X, Y, and Z positions? If we assume that the max position of these two systems is about 2 meters, like I would... This room is not much bigger than 2 meters wide, so it's unlikely that these two systems will ever be more than 2 meters apart from each other. So if we just assume that that's about the limit that we'll have, if we try with just 1 byte of data, the way that you can calculate this is you calculate your the maximum range that you want to have divided by 2 to the power of the number of bits that you're using to encode that information. And in this case, this gives us around 7.8 millimeters of resolution. So if we can say to Ball Butler, like, we want the Z position to be 0 or 7.8 millimeters or 15.6 millimeters. I'm not going to be able to do the next one in my head, but not right now at least. But yeah, so we can only go in like roughly 8 millimeter increments, which is probably fine, but it would be good if we could get a little bit more precise than that. So what if we do 2 bytes? That's 16 bits. This gives us 0.03 millimeters of resolution, which is pretty damn good. Like, yeah, I think we can all agree that is a fine enough resolution for us, to the point where we actually probably don't really need resolution that fine. So what we can do is we can kind of go back the other way and we can bump up our resolution to a point that we're pretty happy with, and then figure out what that allows us to have for the maximum value that we can encode. And what this ends up being, if we have a 0.1 millimeter resolution, which is still honestly probably more than what the system is going to be able to achieve in terms of like the accuracy of the throw, then that will give us a maximum of 6.5 meters in all of X, Y, and Z, which is huge. That is significantly bigger than this room is. So and also that is a finer resolution than what we need. So I feel pretty good that 2 bytes is enough. I could definitely do like non-integer numbers of bytes. I could do like 1.5 bytes for each one, but just in terms of the like understanding of these things, it'll be very handy if I can just have like specific bytes do specific things rather than like this byte is half the X position and half the Y position. That just seems kind of messy to deal with. Craig says, if practical, write the ball ballot inverse kinematics in a way that's easy to run in either place. Then it's easy to run it where it is ever the most useful for a particular activity. Yeah, that's a good call. Yeah, I think writing things in a way that's easy to run that seems like good practice in general as well. Yeah, I agree. Yep, thank you for that suggestion. Yeah, so moving ahead with this, I think it's pretty reasonable to move forward with this and say that each position coordinate will have 2 bytes to encode that information, which leaves us 2 more bytes for time, because you remember that a can frame has 8 bytes in it. We're using 6 for position, so that leaves us with 2 bytes for time. But is that going to be enough? Well, we can figure it out. If we are encoding the time in milliseconds, so if we want millisecond precision for when the ball will land, again, it's up for, I don't know, not really debate. We will find out when the time comes whether we can actually achieve this level of precision in terms of the landing position. I suspect we probably can't, but it's good to, I feel like it's better to have the hardware be the limiting factor rather than the software resolution. So yeah, we can always improve the hardware, I guess. Yeah. And so if we do encode this in milliseconds and then convert from milliseconds into seconds and then from seconds into minutes, we end up with 1.09 minutes, which means that we will not be able to send a command to Ball Butler to throw a ball in 2 minutes because we just don't have enough bits of information to encode that time in the message. But to be honest, that's fine. If you have any experience with juggling, you will know that a minute is a very, very long time for juggling. That is like all the time in the world. You're never going to have a situation where a minute is like, oh, I'm like, it's coming up, you know? Yeah. So this is plenty. Yes. Cool. So this gives us a can frame having the first 2 bytes being the X position, the next 2 bytes being the Y position, the next 2 bytes being the Z position, and the last 2 bytes being the landing time. And we have these limits of like these scales of how much resolution we have on like what each bit effectively represents. And then that we also have these limits of how big of a piece of data can we actually send. And yeah, all of these seem pretty safe to me. Cool. Okay, so that's Jugglebot telling Ball Butler what to do. What about Ball Butler giving the feedback back to Jugglebot saying how will the ball be coming back in? Well, how will it be coming into Jugglebot? Yeah, at all. So this needs to report the landing velocity. And from the plots earlier, which I closed again, why do I keep closing it? From these plots, I actually let me go back to the actual scale. So we have the catch position 1.1. Yeah, you're right. Yeah, Craig is definitely right that the axes should be proportional to each other. Yep. But anyway, we can see that the landing velocity over in this last column up here is around 5 meters per second, which means we won't be able to use the same. Well, if we do use the same scale that we used for the position, we will be pretty close to hitting our limit all the time. And it's pretty unlikely that we're going to be having a landing velocity of like 0.5 meter per second, because that would be like dropping it from directly above Jugglebot, and that's never going to happen. So maybe we could have it like offset a bit. So like the 0 is like 3 meters per second or something. Or we can change the resolution here. And realistically, we probably don't need 0.1 millimeters per second as our velocity resolution. So instead, we can use 0.2 millimeters per second with 2 bytes of data. And that gives us a maximum velocity of 13.1 meters per second, which if we look at the plot, even if we're throwing through the ceiling and it comes back down, we're still only at 7 meters per second. So it's very unlikely that we'll ever have a throw that comes in with more than 7 meters per second. So 13.1 should be heaps. And this, because we're using this wider resolution as well, we can go like all the way from 0 all the way up to 13.1. So we have a very wide range. Like if I move Ball Butler around, so it's like, rather than being like on the shelf up here, maybe I decide to put it on one of the lower shelves down here, or like on the back wall or somewhere else where it's like kind of in line and the ball will be coming in a little bit slower, we can still cater to that. Whereas the only way it's going to be going at 13.1 is if it's like a massive height differential and my room is just not that big. Good question. Fluzzy says, how are you going to ensure that Jugglebot and Ball Butler clocks are in sync so Jugglebot correctly knows exactly when the ball is going to land? Very good question. I should have mentioned this. Yep. So this goes back to, I don't even remember when I did this before. Some time ago, this year, I'm fairly sure it was this year, I had the same problem with Jugglebot itself. So on Jugglebot, we have the main computer, the Jetson, which sits down on the floor beside me here. And then we also have a Teensy that's on the hand. And that the Teensy on the hand does the processing of like the hand, like it basically generates the profile of what the hand motor needs to follow in order to make the ball do what it needs to do. And that processing step is, there's just a lot going on there, which is why I decided to move it off of the main computer and put it on the Teensy as a bit more of like a distribution of labor, I suppose. And I can't remember off the top of my head right now exactly why I needed to, I don't even know if I actually needed at the time to make these in sync, but I basically wanted to, for a very similar reason, because like we need, I think it was for like this same sort of reason, where we need to know, the timing is very important, obviously. Like you seem to be a juggler, you can do 5-ball pattern, which is pretty good. Yeah, you will know that timing is crucial in this. And I anticipated this being a problem later. I don't actually think it was like a problem at the time, but I knew that it was going to be a problem eventually. So I have established this, like, it's called the time sync layer. After this stream ends, I'll put a link in the description to the code where that exists if you want to check it out. And it's essentially on the CAN bus all the time, the Jugglebot computer is broadcasting the current time. Or like it just constantly goes. I think that it's like 100 frames per second or something like that. It's like current time. And the Teensy that's on the hand, and Ball Butler's Teensy will do the same thing, will receive that time and just make sure, and it's also got its own internal clock, and will basically receive that time over the CAN bus and use that to ensure that its internal clock is synchronized with this like heartbeat timer, if that makes sense. This also means that when we send the end effect of this is that like this ensures that these clocks are always in sync within like a couple. I did actually run some profiling on this at the time to see how far these clocks deviated. So like when the new time update count comes in, we can see how much that differs from what the internal clock is saying. And it was within like microseconds of being in sync. Obviously, like it's the first one that comes in, like the internal clock on the Teensy has no idea what the time is when it first boots up. But as soon as that first one comes in, it says, cool, yep, this is the time. And then on every single subsequent one, it just like makes sure that it stays in sync. Yeah. Yes. John says, you needed to sync the hand on the big Jugglebot since the Teensy's doing the high rate commanding to the hand. Yeah. But I don't think it actually needed to be in sync at the time because there's only one ball going on and there's nothing really like causing the need for synchronization. But it was definitely going to be a problem at some point. Yeah. And yes, it is exactly the same as syncing to the Ball Butler. Yep. Yeah, so thankfully that is all already done and I can basically and that's already being broadcast over the CAN bus. So all I need to do is get the Ball Butler Teensy to tap into that and then it'll be in sync as well. I am actually, just a quick aside, we'll see how quick. Actually, no, it's not worth going into that. Yeah, it doesn't really matter. Yeah, but if you're interested in the code, then after the stream ends, give me like an hour or two after the stream ends, and I'll update the description with the code for that, if you want to check it out. Yep. Yeah, so I feel pretty good that these clocks will be in sync. Yeah. Okay. Yeah, so our 13.1 meters per second max velocity is heaps. We're never going to hit that. That's plenty fine. So this means that the canned frame that's being sent from Butler to the Jugglebot computer will have the first byte will be the velocity in the x direction with a resolution of 0.2 millimeters per second. And then we've got Vy and Vz. But this gives us an extra 2 whole bytes at the end that's just empty. And I'm thinking that maybe some kind of acknowledgement signal here could be good, but it's kind of tricky because there's no like ID being given to the throw in the first place. So the acknowledgement can't be like, yep, I'm acknowledging throw number 5. I'm about to send it out as you commanded. But there's no number given to the throw. So I don't really know what the utility of an acknowledgement signal. I don't know how that would be set up in a way that would actually be useful. Yeah, I was thinking of also just including the time again, just as like a redundant thing, and that way, when Jugglebot receives this velocity command back, it can make sure that the time that it commanded the ball to land is the same as when Butler is expecting the ball to land, and as long as they're in agreement, then it's the same throw. Maybe that would work. I don't know, but we've got an extra 2 bytes just hanging out, so we can fit something in there if we need to. But for now, I have no immediate plans for it. Yeah, cool. So that's my plan. So we'll have one can frame to send the ball and one can frame to acknowledge, basically to like give feedback on how the ball is going to come in. And that should be pretty robust, I think. I don't think I've ever had any, once I had the CAN bus set up properly, I don't think I've had any dropped frames at all. So I feel pretty good that just a single can frame out and a single can frame back should be fine. If I do have problems, because this will be a much longer length of CAN cable going up to Butler, so it's possible that there'll be more noise or something in there and we might have dropped frames. So maybe we'll have to have a bit more like error correction and like checking to make sure that the frames actually get through. Maybe, but I feel pretty solid on CAN at the moment. So I think that this structure should work quite well. And it's so efficient as well. It's just one frame back and forth and that's it. Compared to compared to even just that time sync layer, we've got 100 frames going back and forth just for the time. Like, yeah, this is very minimal, I think. Craig says you can put a checksum. Oh, this is a good idea. You can put a checksum of the initial request so it can be used to pair request with response. That's a cool idea. I like that. I'll have a think about that. Yeah. And John says, CAN messages are only 125 nanoseconds apart at 1 megabit. Are you sure you need to pack this in a single message? Maybe not. I mean, like I'm from memory, I think I have on the order of 1,000 or so messages going back and forth on the Jugglebot CAN bus every second. It's like I think it's around 1,000 all the time. So yeah, I think we've got a bit of headroom above that as well. So we can definitely use more frames than just the single one. But like, why? Do we need to? As far as I can tell, like this information is plenty. Like if we're going from Jugglebot to Butler like that is all the information we need. So I don't really know if we need to split it up a bit more. We could. Okay, what I was going to say before as the aside is that when I am sending commands to Jugglebot to make, like when I was doing the catching cone thing, when I'm sending that command out, I have 4 bytes to encode the time, which allows me to send a command to Jugglebot within the next, it was around 50 days. So I could say, hey, Jugglebot, make this throw in 2 weeks' time. And as long as everything still stays on, it'll just sit there and wait until 2 weeks' time has passed, and then it will make the throw. Which is a bit overkill. But however, 1 minute is like, while it is like a very, very, very long time in terms of juggling, it's not objectively that long of a time. So it could happen maybe that we need to extend that time out a little bit. So if that ever happens, then yes, it will be necessary if we want to keep the same structure for the rest of these, it will be necessary to expand this out into 2 frames, in which case, as you say, John, yeah, that's going to be absolutely fine. Okay, John is saying, I was thinking about to use 4-byte floating point values, and then you cannot worry about ranges and precision, yeah, can't say that word right now, so much. Yep. That's a good point. Yeah. But like, I don't know. This is pretty fine. And this is also very similar to how I have been doing other transmission of messages where I've got like a set resolution, the sender knows that, the receiver knows that, which is a bit of a, that is something that I do just need to make sure is like in agreement between the two systems, which is maybe a weak point of this system. Like I need to make sure that both Butler and Jugglebot are in agreement about 0.1 millimeters being the resolution, because it's not going to be sending 0.1, it's going to be sending like 1, and 1 is equivalent to 0.1. So they do need to be in agreement about that, and that is, yeah, not super robust. So maybe you're right in that regard, that if I just use floating point values, then I won't need to do that at all, and it can just be the value is the value. Yeah. Yeah, okay, I'll have a think about that. That's a good point. Okay. So, the next layer of things, I suppose, is how will Butler think? And we could use ROS. And I am so torn about what to do here. But I'll get into my thoughts in just a second. So we could use ROS because there's a thing called ROS Serial Arduino. And the serial part of this I'm not super pleased with, because I've not had good experience with this serial, especially because we're going to have like probably like 2 to 2.5 meters of cable between these two systems. I've been having problems with serial with like a 50 centimeter long line. Big difference there. So we're going to have probably a fair bit of noise if we use serial, but I don't know if there's like special error checking stuff in the ROS serial thing, but in any event, this is an option. Or we could not. So my thinking here is, on the one hand, ROS has a bunch of libraries for simulating robots that I haven't been able to use so far because they cannot handle parallel robots like Jugglebot, where you have like the base, some number of actuators that are all connecting to the base and are all connecting to some end effector, like what Jugglebot is. They can't simulate that for whatever reason. I can kind of see how it's a little bit more challenging, but that's not my domain, so I'm not going to comment too much on that. But suffice to say, you can't do that sort of simulation in ROS right now, at least, as far as I'm aware. You can, however, simulate serial robots, where you have the base, you have some kind of actuator that attaches to another actuator, that attaches to another actuator, and like the first one moves all of the other ones down the chain, which is exactly what we have in Butler. We have the base rotates around, we have the pitch axis, moves up and down, and then we have the third axis will throw. And they affect each other in that order. So this type of robot is very amenable to being simulated in ROS, which would be a very good experience for me to get practice with that and to familiarize myself with these simulations. So on that side, that's very tempting for me to have those simulations working, and then I can try some like sim to real stuff where we can like simulate the behavior of Butler, and then like, I don't know, have like a neural net that controls it. This is maybe a bit overkill, but yeah, basically getting familiarity with this type of workflow, which I haven't done before and I am very interested in getting familiar with. On the other hand, ROS is the only thing that I've been using since I'm going to ignore the stuff that I was doing right at the start because I had no idea what I was doing. But once I kind of started to get a bit of a feel for like how robot control actually works, ROS is the only thing that I've been using that whole time. And so I'm kind of like, I don't know what the right analogy here is. I feel like ROS is the only thing that I know. And also, there have been a lot of people for Jugglebot as well as for Butler suggesting that there are other platforms to use that are a bit less kind of clunky. Like, there's a bird going off. ROS is quite clunky. There's a very steep learning curve. There's so much like infrastructure that you have to set up for it to work, and you have to use it in very particular ways for everything to kind of like flow nicely together. And yeah, it's I can definitely understand why people kind of consider it to be a bit clunky. Whereas other suggestions that people have seem very elegant, very clean, I mean, this is all just like my observations from not having used them, but people really are advocating for other types of approaches. And so and like, that is another thing that I also want to really learn about. And like the fact that like no one in industry really seems to be using ROS is like a bit of a red flag in my mind. Like, why does industry not use ROS? Like, yeah, I know some of the arguments for and against, but yeah. Suffice it to say, I'm interested in ROS for the simulation aspect to learn about how that works. And I'm also interested in non-ROS to just see, now that I actually understand what ROS is doing, and now that I have a bit more of an understanding of what is involved in getting a robot to work properly, I'm kind of interested in doing that without ROS on a very small platform like Butler. Like, it's so much more simpler than Jugglebot is. So this feels like a good test platform to experiment with this other way of doing things, or one of the other ways of doing things. Bad Boy says, what if I build a ROS driver for it? You do it without and we can compare. I have lots of thoughts on why the industry does not use ROS. Very interesting. Okay, Bat Boy seems like a big fan of ROS. Very interesting. This seems like a good discussion to have on Zulip. Yeah, so, I think you just signed up to Zulip recently, I think. So definitely, yeah, post your thoughts on there and I'll have a look. Yeah, I agree as well, actually, that because this is a much more simple platform than Jugglebot is, this could be a good opportunity to test multiple options. So we could try without ROS and could try with ROS and kind of see what the difference is. Maybe get the best of both worlds, potentially. But then there's the other side of like, this is just like a little side project. This is not like the main thing. Like, this is just to help Jugglebot and to help me. So with all of this, I don't really want to be spending like a crazy amount of time getting this to work. However, if you make the driver, that's definitely a big push to use ROS. Okay, we'll see how it goes. But at the time of writing these slides, I'm opting for the latter, to not use ROS. Yep, we'll see how we go. Okay, next thing. I'm gonna have a drink of water first. Finally, I have made proper updates to the schematic. It is definitely about time. Some time ago, I showed off, this was my operating schematic for quite a while, and this did not bring me joy. Every time I had to open this up to like either see how things are connected to each other or to just like update it with new connections, no joy was had. Terrible thing. Big poo. Don't like it. So I decided to finally bite the bullet and actually do this properly. So I have made this in KiCad, I don't know. I'm going to go KiCad. Because if it was KiCad, it'd be K-E-Y, I feel. Anyway. So I've made this schematic up. I haven't finished it yet, and you'll see there's a bit of a gap over on our throw axis, but I have something to say about that in a second. But everything else in here is correct. So, and it's just so much easier to read. Yeah, so we've got like the CAN cable, big picture, we've got in the blue box is everything that's inside the base. And then in the green box, we have everything that's outside, that's above the base. And connecting the two together, we have a split ring that's running with 12 volts, CAN too high, CAN too low, and ground. And I have a link in the description as well for this schematic if you want to check it out yourself. Both the KiCad, I'm going to just alternate between them, I guess. Both the KiCad folder and this PDF as it is right now. Yeah, so the general gist of what's going on in here is we have the CAN cable coming in. This is CAN 1, as I'm calling it. So this is coming in from Jugglebot, and this is what's coming in through the... currently there's only two cables in here, but there will be two more soon. That's what's going to be coming in through this connector in here. And that will bring with it 12 volts, ground, CAN high, and CAN low. That goes into a CAN transceiver, which then goes over CAN 1 RX and CAN 1 TX into the Teensy. The 12 volts and the ground goes into a 12 to 5 volt buck converter. I don't know what the part number is for this. I've tried to include as much information for all of these parts as I possibly can. So we've got like part numbers and like very specific information on all these things. So hopefully my intention is that if someone else wants to, I don't know, make use of this like work that I've done, you can hopefully find all of these components yourself. However, I have no clue what component this buck converter is. Let me quickly grab one actually. I bought like 10 of these some time ago, and I cannot find them again. They're just like random, no-name brand. They go from 4.5 to 20 volts in, and they have an adjustable output, which I really like, so I can use these in various contexts. And they seem quite good. Like I believe I've checked the output of them, and it's like it's clean enough for what I'm doing, but it's just a bit annoying that I can't find them again to get more of them. Yeah, so that 12 volts comes in, and then this spits 5 volts out, which then goes into the teensy to power the teensy, and I think that's it. I need to check some stuff because one, to skip ahead a little bit, the teensy is taking 5 volts in, and it's putting out, one of the pins on it is to output 3.3 volts, and I'm using that 3.3 volts to power the CAN transceivers because they are powered off of 3.3 volts. And it should be powering the yaw encoder because that yaw encoder, we can see, is plugged in to the teensy as well. So we've got like the yaw encoder's SPI lines are going into the teensy, and they should be operating on 3.3 volts. As far as I'm aware, like the teensy is, nominally they say that the pins are not 5 volt tolerant, but according to my photos that I've taken, like you may remember, I cannot easily get into the base of Ball Butler right now because I haven't printed off the hinged base yet. So I can't get in there to actually see how this is wired up, but my photos suggest that this is actually, the yaw encoder is actually being powered by 5 volts, in which case I have no idea how it works because that should break the teensy, at least those pins. But it should be powering, it should be powering the yaw encoder. Yeah, we then also have a second CAN transceiver that powers the Ball Butler's internal CAN, which I'm calling CAN 2, and that one just connects to CAN 2 on the teensy. Pretty straightforward. And that also goes to like these CAN 2 high, CAN 2 low, which goes through the split ring. So yeah. And then also inside the base, we have the yaw axis. So we've got this brushed motor driver and this Pololu brushed motor, which I've been like using this like Pololu products for like literally years, but only last night when I was typing out this part number did I realize that it's actually Pololu, not Polulu. I thought it was P-O-L-U-L-U, which sounds so much, Polulu sounds so much better to me than Pololu. But anyway, I digress. And that's wired up in this way with like the B's and the A's being connected up so that we can have more current, even though we probably don't really need it because it's not really pushing very hard. And it's also like massively geared down. But we also have this yaw encoder, which is wired up in the way that you can see. This MOSI connection is required for the SPI to actually work at all. That's something that I've forgotten to do a number of times, and it's frustrating every single time I do it. But yeah, so that's everything that's inside the base. And then above the base, we have the pitch axis. We have an O-Drive Micro wired up in much the same way as the yaw axis, but instead the load encoder is going straight into the O-Drive Micro, and we are using the onboard commutation encoder. And we can see the motor here is the Eagle Power. We then have the throw axis, and I will talk more about this in a sec. Yeah, so this is so much better. I don't know how, I don't know why I thought this was a good idea to do this. And like, honestly, it actually didn't even take that long to put this together. It's been a long time since I've used KiCad, so I'm going to stick with KiCad. That's easier to say. Well, although we'll see. It's been a while since I've used KiCad, so it took me a little while to like familiarize myself with it again. And I ended up making all of these symbols myself just to like fit exactly the context that I wanted. And yeah, so it did take a little bit of time, but it's so worth it. Like this is so much cleaner and so much more informative than this, because this is like, okay, cool. This yaw encoder is attached to the teensy, but like how and on what pins? And it's been such a it's actually caused problems with me before where I'm like, hang on, which CAN bus is the teensy, which CAN bus on the teensy is the one that's like internal to Ball Butler? I'm like, is it CAN 1 or is it CAN 2? And according to my diagram here, I don't know on the teensy. Like I've got this note up the top here telling me this information because I forgot it a couple times and I had to like check my code to find what numbers they were. But here it's obvious. Like CAN 2 is CRX2 and CTX2. CAN 1 is CAN 1. So much better. definitely recommend doing it properly. Spend a little bit more time on doing it the right way, and then you just don't need to worry about it again, and you get all the information that you want all in one place. Yeah, so I still have a little bit of work to do on this to like neaten up the teensy. I need one to like put a box around it. I'm going to add some more notes in various places for different things, but yeah, hopefully this is a lot more useful for anyone viewing and also just for myself. Yeah, so feel free to check that out if you want. Okay, now this is the thing that a little bit broke me, a little bit. This is the most complex part I've ever modeled, I think. It's definitely got the most number of features. So there's a link in the description for this version of Butler as well if you want to check it out. But essentially, oh, okay, my mating is broken as well. Let's just look at this. So what I wanted to do is, for some context here, I'll go back to this. Previously, we had the ODrive Micro was powering the hand motor. In principle, I pretty quickly figured out that the ODrive Micro, well, it was a bit too late. Once I actually tested it, I very quickly realized that the ODrive Micro was not sufficient to power the hand motor. And at the time, the only other ODrives I had were ODrive Pros. And we know that the ODrive Pro works for this hand motor because that's what Jugglebot is using. So I figured, okay, cool, we'll just do what we know works, and I'll use the ODrive Pro with the hand motor, and we should be fully hunky-dory, everything will work nicely. And I spent a very long time making this black part so that we can fit the ODrive Pro nicely in here, as well as having the hand motor be on like basically to have the hand motor to fit properly. And my God, this part is so featureful. It is very feature rich. I think we're at like 140 something features. 143. Damn. It's got a lot going on. There is so much in this that it's responsible for. But the gist is that we want the hand motor to have some kind of encoder on it so that way we can actually control it. And we need it to be able to move the hand up and down. Originally I had the hand on this surface up here, so it was running up and down here. But if you remember the result, the result of our simulation of like what throws we should be making, we probably want Butler to be capable of making very low inclination throws. And if we have things set up, if we have the hand set up the way that it is here, if we try to tilt down, will this break? Let's find out. If we try to tilt this down, okay, I think I've set very conservative. Maybe I can fix this. Oh, you can't fix stuff inverted. Anyway, you can use your imagination. If we tilt this arm down and slide the hand down, it's going to hit the base. That will not work. So we are not able to make very low inclination throws with this structure of hand. So we need it to be on the side over here. And of course, even as this is right now, if we tip this right down, and there's nothing, the only thing stopping this from going further is just an arbitrary limit that I've set in here. Let's go, I don't know, let's just go huge so that we can, you can't change inversions. All right. Yeah. This can go further down, but obviously like we would need to change the structure of the hand, because if we do this exactly as this is right now, the ball's just going to fall out of the hand. But that should be a pretty easy fix. And yeah, for that to work, I had to do a bit of shenanigans with the motor to get it to fit nicely. And yeah, it was a bit of a process. Lots of back and forth and mucking around to try to get this to work. Also, in case it's not obvious, the reason why I have the 3 strings here is to represent what it will look like when the string is like most wound and unwound on the different sides. And there is some weird stuff going on like in here. This is obviously not how the string would actually go because it can't just pass through the pulley, but making that do what it's actually going to do is very hard to do in CAD. So I'm just assuming that I'm just kind of going off of vibes for this kind of thing. And my vibes tell me that this is probably fine. Yeah. This is also like the orange and the white lines are also like 1.3 times what I'm expecting them to actually be. So they should actually be a little bit closer to the middle, because this stroke here is so short. So there's actually really not that much string that actually needs to be spooled and unspooled. Yeah. Yes. And yeah, so I want to give you a bit more of a picture of to explain some of the other things that this part is doing. We have a couple pulleys in here. Maybe I can just go to the part itself. Maybe this will work. Actually, no, you can't see the context. Yeah, so we've got the string that comes down, this guy here. I wanted to make sure that it was out of the way because we need to make sure that this spool for the pitch axis is supported. And the best way that I came up with to do that involves having basically that spool has two bearings on it, and those bearings are supported by this bracket, and that bracket now clamps onto the outside of the aluminium extrusion. So now I don't need to drill any holes in the aluminium extrusion, well, any more holes in the extrusion, which is very nice. I quite like that a lot. But it does mean that the string can't stick out past this point because it's going to hit that bracket. So I needed to reroute it so that it goes like inside the extrusion, like inside that cutout in there. Maybe this is a good way to see it. Yeah, so it's very nestled in there. And to get that to work, we just have, thankfully on this side, we only have one pulley here. And yeah, string just goes up. It then comes out around, oops. Maybe actually I'll do this face. Come on. It comes out around, that was definitely not the fastest way to do that. Out around this pulley, just so that we have enough clearance to get access to this bolt, which is used to increase the tension here to make sure that the line is nice and tight. So it's definitely a lot more complicated of a routing than what we had before, where it was just like the string just goes up and around and then over the spool. Like this was so simple. But we can't have this simple of a routing when the hand is on the side, because that means that the motor will be hitting the ring. So we can't do that. Yeah. Yep. So then we have the supports for the motor, and also for this encoder, and this is the same encoder that I'm using for the pitch and the yaw axes. This is an SPI encoder, which I have plenty to say about in a second. But those cables will come up, they run through this cutout in here, they run through this channel over here, and they plug in. That perfectly lines up with this blue connector here where they connect up. And yeah, so that should work pretty nicely. I'm planning on using the same kind of cable structure as what I have in the currently existing design, where we've got the cables coming out from the bottom. They rest inside this groove in here, and that way, and then they connect up to like the top of like what is now like this new part. And that way, as this moves up and down, that cable allows for that motion to happen and also keeps nicely out of the way and tucks up very nicely when it's fully vertical, which I'm a big fan of. And yeah, so in the same kind of way, we have the cable will come up through this channel here, and then that will come up into this groove. I should have added a slot for a cable tie to actually like really properly secure that in. But then that channel extends down. It is a little bit bisected by the O drive. The O drive kind of sticks out a little bit into there. That's kind of hard to see, but yeah, this corner here is from the O drive. That channel then extends down through and I was planning on using the same, well, I am planning on using the same bus bar approach, where on the current one, we can see up here, we've got these screws, and these are what I'm using to connect those 4 lines that are coming up through the split ring. So we've got can high, can low, power, and ground. And those are all bus barred onto here, and that makes it so easy to connect and disconnect things. And like, yeah, if I need to change any wire lengths, I don't need to change all of the wires, I just need to change that one part. So good. Yeah, so I'm planning on doing the same sort of thing here, where I have can high, can low, and then power and ground. And the reason why the power and ground are so separated is because I need, I think I needed to route them in a different way. For some reason, oh, that was it, yeah. So I need can high, can low. are easy because like the CAN signals are coming into these two guys here. So like these are effectively the same plugs. And so I'll have CAN high, CAN low go into one of them. And then the other one will be used to kind of like daisy chain that signal up to the ODrive micro. So there'll be a cable running from like this white connector up to one of these blue connectors to extend the CAN line. But power, the two power lines, the 12 volts and ground, those will need to run up to the ODrive micro as well. But they also need to go back the other way and connect into the power side of the ODrive Pro, which is back over here. So we'll have those two, like 12 volts and ground, will come back through this channel shared with the SPI lines, which is not ideal, and going into the ODrive Pro over here. Is the plan. And like definitely in hindsight, I really could have made this channel a bit bigger, but it doesn't really need to be. Yeah. And it worked. It prints. It's very nice. I have my encoder on here. I've got my nice braided SPI lines that come up through the channel. That worked perfectly. I perfectly measured out the length of those lines so that way they plug in very nicely into the connector on the Pro. It's so clean. It's so nice. The print quality is a bit crap because I did not design this for printability at all. And in hindsight, I really should have just made this so that the whole thing could just sit flat, because the way that I printed it here is like this, where I from memory, this surface and this surface, yeah, they're parallel. So like it sat on the ground like this on the print bed. And like realistically, there's no reason why this needs to incline like that. Like I should have made this completely flat so that it prints a lot nicer. Yeah. Yep. There were some oversights that I had in terms of printing, because like these holes in here are very involved and they're very, very close to each other. It took quite a long time to get these pulleys to be able to be mounted properly. So my plan is to have a dowel pin through this hole that secures this pulley in here, and then this pulley over here is just secured by a single bolt. And thankfully there's enough space in there to get them to fit. However, as part of my modeling process, as I made this, and this is obviously like there's a link for this, so you can check this out in as much detail as you want if you are so inclined. But I've got a picture. I don't know how to show it easily. Let me change my camera for a sec. I'm just going to screenshot the screenshot. Yeah, so what I did to make the section where the... Sorry, I just need to catch the slides back up. Okay. All right, yes, cool. All right, so what I did to make this section where the pulleys extend is, we can see if I roll to here, I had much the same structure as what I had in the past, where it was just cut out like this. But that section, to get those last pulleys to fit nicely, was a bit of a thinking process. It took a while to come up with a good way to do that. And I found the way that I ended up going for it was to basically make a separate part, make all of the features that I want to make. Oh, okay, I haven't got it rolled back in the right way. I don't know exactly where the features were where I did this, but I made all of these features that like support these pulleys and the motor as a separate part, and then did everything that I wanted to do, and then I booleaned them together. But when I did that, I didn't check carefully enough that I had ensured that all of these holes were still through holes, and I ended up blocking some of them off, which was very frustrating. And I only realized this after I printed it. So like this here shouldn't be there. That's just because I had one part and booleaned it into another part and forgot to move those faces. And like that cutout there should not be there, which means that I cannot, and this is this part that I printed here. So like those holes don't go through the whole way. And of course I can't get my drill in there to like extend them out because this other crap's in the way. So unfortunately Unfortunately, I can't actually use this to test whether that pulley mechanism actually works. I'm fairly confident that it will, and that the string will coil and uncoil quite nicely, but I can't actually test it unless I print this again with these fixes made. But the reason why I haven't done that is because of the real problems with this design, which is that all of this might be for naught, which is so frustrating. This really drove me mad. I was not happy about this. How can I show this? Yeah, okay. So there's a couple problems that I would have realized were problems if I had done a bit more testing beforehand, before jumping into the CAD. I am too CAD happy. I'm a happy man when I'm doing CAD, and I'm so eager to just like jump into the CAD and be like, yeah, no. The thing that I'm designing, like I can make the thing fit what I want it to fit, but I'm not giving enough. Well, I didn't give enough thought to the electromechanical side of things and whether that stuff would work, because I've just been assuming that it will, and it did not, for a couple of reasons. One big problem for this design as I have it here is that this encoder that gives me that I'm using as a commutation encoder for the hand motor is using SPI cables, or SPI like signal. And it just seems so dodgy. SPI seems very noise prone. It's not very robust against noise. And because I have it running, I think because I have it running right next to the motor phase cables, and also I haven't included in here yet the power cables that are going to the ODrive Pro, there's a lot of other cables running around this SPI line. And either because of that or because of my wiring, I think that my wiring is fine. Like, it seems like I spent a long time making sure that I did it right. That connection between this encoder and the ODrive Pro, it just keeps dropping out. Like, it will work and then it won't work, and I'll have to like unplug the ODrive and like plug it back in for it to establish that connection again. And it just seems very droppy. Not very reliable at all. And that is without the ODrive, without this motor even being on. That's just purely reading the values of what position the motor is in. So yeah, and like once it gets moving, then it's like only even less reliable. So the easiest solution there is to change the encoder to a different type of encoder that's a bit more noise resilient. I don't really know what I would do there, so if you have any suggestions, I am very eager to hear them. But that's one option, is to change the encoder for a different encoder that's mounted in the same spot, but just has a more robust communication. Keeping in mind that this is probably about a 15 centimeter long span between here and where it connects to on the other side. So it'll have to be able to be robust for that length. I could also try this same line. I believe I have some 5 cable shielded cable, so I could try that instead of just like the raw unshielded cable. That might help. I might give that a go depending on how I feel about wiring that up. Yeah, potentially. But an even bigger problem with not strictly this design, but like my thinking writ large for this whole system, which is that my plan so far has been to use just the CAN cable to power the entirety of Butler. And that CAN cable would be carrying 12 volts, CAN high, CAN low, and ground. And that 12 volts is the same, it's like the same cable that's connected to Jugglebot, but Jugglebot is not really drawing any current from it, which is quite nice, which means that we have about 3 or 4 amps of current from the power supply that is powering that 12 volt line just for Butler. And just looking at a raw like power use side of things, that should be fine. That like 12 volts at 3 amps is what, 36 watts? And I mean, if my calculations are correct in here, then we only need like single digit watts to actually throw the ball. So that should be completely fine. However, I have again underestimated how complicated brushless DC motor control actually is. And once I tried spinning the motor up really fast, it was dropping the voltage of my bus. And that's not usually a problem. Like on Jugglebot, I'm sure that the same thing is happening in that like the instant where the hand motor is accelerating to throw the ball, I'm sure that the voltage on the bus is dropping quite a bit, but it's not a problem because that bus is running at 45 volts and the default warning for like the under voltage on the O drives is 10.5 volts. But you'll notice that 10.5 volts is very close to 12 volts. And in all of my testing so far, where I have been running any of my O drives with the hand motor, and as soon as I try to accelerate it quickly, the voltage drops below 10.5 volts and the whole thing shuts off. The O drive shuts off. Which is so frustrating. But there's nothing I can really do about it except for figure out some solution. So what this means in my mind is that I can't use 12 volts to power Ball Butler. Well, at least to power the hand motor. I need more than 12 volts so that we have a bit of headroom to allow the bus to drop a bit when that hand really ramps up, and so we don't have any issues. Yeah, so I need to figure out some other way of powering the system. I have, while I've been going through this, I have realized that the power supply that is providing power to Jugglebot, which is the 45 volt power supply, is actually like right beneath my finger here. It is right next to the shelf that Ball Butler will sit on. So I'm thinking that perhaps the easiest option will be to take the 45 volts from that power supply and just run it up the side and into Ball Butler, meaning that Ball Butler will no longer be using the 12 volts in ground. Well, it'll probably be using the ground just to... I'll have to think about how I should set up the grounds to make sure that I don't have any ground loops, but it means that the entirety of Ball Butler will now be powered off of 45 volts instead of 12, which should only change a couple things. I will need an extra stage of voltage reduction to power the teensy and everything, because my current buck converter can't go that high, but I think that shouldn't be too hard to overcome. The other option is also I could use a battery, and you may remember the batteries are something that I have been a little bit spooked by for some time, but it's another thing that I'm curious to play around with. So yeah, I think realistically, I think what I'll probably end up going with is just powering off that 45 volt power supply and just running it up to Ball Butler. Maybe, but it's just frustrating that I didn't do more testing before. Yeah, realistically, yep. And okay, one other thing that is giving me, I don't know, pause on this design here is that using the ODrive Pro, you may recall that I don't want, well, using any of the ODrives that I've mentioned so far, I don't want to have any, when Ball Butler throws the ball, it will accelerate really fast to throw, and then it will need to decelerate really fast to slow the hand down to make sure it doesn't just like smash into the end. I have considered using a mechanical end stop with like a shock absorber or that sort of something along those lines, and I'm still very open to that, but that is very, it's quite different to anything that I've done before, and I don't know, I'm not familiar enough with brushless DC motor control to know how that could work to not give the ODrive, to not like freak the ODrive out and make it throw a bunch of errors that cause the system to kind of stop. So the easiest solution in my mind is to do what we've been doing so far and make the hand electromechanically brake so that the ODrive like will actively be slowing the hand down, but that means that power is going to be sent back over the bus, which I really don't want to do because that will probably damage something. This is where, enter stage left, I recently bought some ODrive S1s. And these ODrive S1s seem to be, I've done a little bit of testing, and they seem to be powerful and like capable enough of powering the hand motor in a way that the ODrive Micro was not. And even better yet, they have a port on them for a brake resistor. So these lines down here, we've got like the motor lines, the DC power in and out, and these two here are for the brake resistor. So I can have a brake resistor directly on the hand, and that means that we can do as much regeneration, well, maybe not as much regeneration as we want, but as much regeneration as Ball Butler will need, and that power can just go straight into the brake resistor and then get dissipated by heat. So then we won't need to do any mucking around with mechanical end stops or anything like that. We can just do simple control the same way that I have always done it, and that power just gets dissipated back through. Honestly, probably the best solution is probably a mixture of both of these, where I can have a mechanical end stop just to allow us to like really push the limits of what the motor is capable of doing without risking breaking anything, as well as electromechanically braking and just sending that power back over through the brake resistor. Yeah, but of course, if we change to use an ODrive S1, I've designed this for an ODrive Pro. Which originally, as soon as I realized that, I was like, oh no, I've like spent so much time getting this design to work. If I change the ODrive, it might have other implications, and I might need to do a complete redesign of this whole thing. Potentially. Until I realized that clever ODrive people designed the ODrive S1, where if you if you add the heat spreader plate, which like helps dissipate the heat generated by the motor control, if you add that spreader plate, it's the exact same footprint as the ODrive Pro. So I think I should be able to fit the ODrive S1 and a brake resistor in essentially this same spot where the ODrive Pro is. So hopefully it won't require a redesign of this. But back to the encoder thing, if I can't find an encoder that allows me to run the signal lines from like over here where the encoder is mounted up to the controller, the safest option in my mind that I know for a fact will work and will be very robust and will be a lot less, in some ways, it will be a lot less hassle, is to use an onboard encoder on one of these ODrives. But that requires having the ODrive be in line with the motor. The ODrive would need to be like here. And if we have a look in the CAD, and you can use your imagination, you can see that there's not a lot of space in there. Like if we... okay, yeah, I can't edit this because maybe it's worth just going back to here. Yeah, if we add in an ODrive S1, oh nice, it's on the right page. We can see that using the onboard encoder would require a fair bit of a redesign to get this to work. Like if I basically replace that encoder, if we go from, come on Onshape, select the mate. I don't know why sometimes it takes so many clicks. Yeah, there's not a lot of space in here, and I've given a fair bit of thought to this, and I think it is possible, but I also think that I'm a bit of a masochist when it comes to CADing things sometimes, and I think that this could be done, and like there's no reason why this motor needs to be perpendicular. Sorry, it needs to be parallel to the linear rail. We could, maybe not easily, but feasibly tilt the motor on an angle like this, and that will give a lot more room for the ODrive to sit above it like that. So that's on my mind, but I don't really want to do that because I feel like I've punished myself enough in CAD so far. The ideal solution in my mind, I know I've been waffling a bit, but this is just how my thoughts are right now on this structure. Ideally, there is some type of encoder that I can put here that is not much larger than the 5047P that I'm using right now. If it is too much larger, then I'll probably have to do something similar to what I just described. But hopefully someone can suggest, or I can find some encoder that will fit in roughly the same spot and be like roughly the same footprint that won't be susceptible to noise. And then I can use pretty much this exact part as it is right now after I design it to be a bit less printer unfriendly. Yeah, because I do like this. I think it looks cool. I think it's fairly elegant. I think it could probably be a bit better, but got to draw the line somewhere. Yep. All right, I got to let my cat in. Come on. He just scratches at the door for so long until I let him in. Little rat. All right, I've got one more thing. Go on the floor. One more thing for you all, which is something that I'm very excited about, but at the same time, this on top of like all of these like ODrive problems, this is really this is like the cherry on top of breaking me on like Tuesday and Wednesday. So I recently bought a thermal camera, which I am a big fan of. It is very cool, and my plan was to have some way, and I'll show you what this all looks like in a sec. My plan was to have some way for me to have this on somewhere around my desk. So like if I'm doing stuff on my desk that I'm expecting to want to check the thermal properties of, like doing PCB work, or like, At one point when I was testing the ODrive S1 powering the hand motor, I've got this little setup over here. It's kind of wired in. Actually, I can show you on the other camera. Ha 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 ha. That one? Yes. So I've got this set up here where I have the ODrive S1 is connected to the hand motor, and I was doing some testing with this, and a little bit of magic smoke came out, and I don't know where that magic smoke came from or what really caused that to escape, but it would have been very convenient if I could have had my thermal camera on, like watching this to kind of see where the hotspots are and what might be causing this problem. And you can see I kind of have it set up here. So, Albie, not right now. So this is the camera itself. It is very cool. I am a big fan of it. It's compatible both with Android and with Windows 10. It's super nice, and I'll show you what the software looks like in just a sec. But my plan was that I could have it mounted on one of these, like, the coolant tube arms, and that way I can like move it around to go wherever I want to. And I actually have a link in the description for this video of a video that I found of a guy who did exactly this with exactly this camera, and it's so clean. Like, he can just like bring it over and position it wherever he wants. And because this is like such a small, light thing, it doesn't really, in his setup, it doesn't mess around. Like the coolant tube is able to support it, and he can just position it where he wants. When he doesn't want it, he can just move it out of the way, and it's gone. So good. So I tried to make the same thing, and this is driving me mad. So I made this tube here. Let me zoom out a bit. Well, my first attempt, I didn't pay enough attention to how this guy had his setup, and I thought that he ran the USB cable through the coolant tube, and I was like, okay, cool, that's fine. I can just cut the cable and feed it through the tube, and then resolder the cable, and we'll be good to go. And it'll be so elegant, so clean. Leave me alone. And such a good setup. Little did I know how many cables are in a USB 3 cable. This camera needs USB 3. It doesn't operate just over USB 2. But as soon as I cut my USB-C like 3.2 cable, I instantly regretted it, because there are a lot of cables in there. And I was kind of hoping originally that I wouldn't need to resolder all of them, but through testing and like trying different combinations of cables, I ended up just committing, and I was like, okay, fuck it, whatever. I'll just solder all of them together. I think there's 16 in total from memory. I soldered all of them together painstakingly, made sure they're all connected up very nicely through my coolant tube, so that way I can like adjust it to whatever position I want. It'll hold the position. We've just got the female USB-C cable here. Perfect, so good. But it doesn't work! For some reason, USB 3 seems to be very sensitive to the lines. I don't know if it's the inductance or resistance or capacitance or whatever it is. For whatever reason, my soldering has not worked. And if I plug this in, I believe like power goes through, but there's like the signal doesn't go through. Like the camera will turn on and like its light goes on, but there's no data coming back and forth. So I actually do have a USB-C testing thing, but I haven't, it's a bit of a long story. I haven't been able to actually check what connection in here isn't working, but this setup as it is not working. And I'm like, God damn, like, and I don't know. As soon as I cut the cable, I was like, oh crap, maybe this is not what the guy did. So I went back and actually checked his video, and he actually didn't cut the cable. He actually ran the cable parallel to the coolant tubes and then just wrapped the whole thing in heat shrink. That's a much better solution. A little bit less elegant, but so much easier. And I was like, okay, fine, I'll do that. I'll get my coolant tubes and I'll run the cable parallel to them so I don't have to cut it. And I don't really like the look of the heat shrink, so I'm going to use this like the cable wrapping stuff that like, yeah, just a normal cable sleeve sort of thing. And that's what I've got here. But unfortunately, I don't know if it's like a quality control thing with like the dodgy coolant tubes that I bought, but they're not stiff enough to, they can't even hold their own weight up, let alone the weight plus, their own weight plus the little camera. So, in my great thinking, I was like, all right, if the coolant tubes aren't enough to hold it up, maybe I can add some of this. I've got like spring steel wire that I chucked in the end of here, and that's definitely a lot stiffer. Like, if I move this out of the way. That's definitely significantly stiffer, but it's kind of like too stiff now. Like I can't like bend this around, and it just doesn't like hold its position. Like it's so floppy and kind of crap. And this is just, it's so close. This is like, it's long enough for me to be able to like position it anywhere over my desk so that I'll be able to like monitor the temperature of like whatever I'm looking at, but it just doesn't hold itself up. And so I'm thinking that maybe the heat shrink is actually a good idea, because maybe the heat shrink like compresses the coolant tube enough to like force it to hold its shape, and it doesn't allow it to bend. And I think my spring steel wire, like let's just take this out because it doesn't need to be in there anyway. I added 2 parts as well because 1 wasn't enough, but 2 is apparently too much. But just to like, it actually does hold its shape when the camera is not on it, but as soon as I connect the camera into it, it doesn't hold its shape anymore. But anyway, I want to show you what this actually looks like, because it's such a cool device, and they're so cheap as well. I believe this was like $350 or something for the camera. It's so good. I definitely recommend. I've already found some. Yes, as soon as I connect that up, it just flops. It's too heavy. Let me plug it in, and I'll show you what this looks like. Yeah, I've already found some things that I wasn't aware of, like the motion capture cameras that I have in my room. When I'm not using them, they're just like ambiently sitting at like 30 degrees. And now now that I know that, I'm probably going to turn them off when I'm not using them. Like there you go, you can see there's cameras up there. Where are we looking? There's me. Hello. It's so good. Like you can do so much cool stuff with this. Like, let me zoom in a bit. You can like make a line, and you can be like, okay, what's the temperature along this line? And you can like graph it somehow. I haven't played around with it as much as I want to, because I haven't been able to actually get it to like work the way that I want. But on the phone app, you can like draw a line, and it will like plot the temperature over that line. And you can do things like making a plane, and it will like report the highest and lowest temperatures in that region. It's so cool. It's such a handy device. And yeah, so now I'm like, oh, like cool. My cameras are just sitting there like wasting energy all the time when they're not using them. Like how warm is my light? So good. And so my older brother as well is a like civil engineer. And when I showed him this, he was like, damn, like I have to get one of these, because apparently you can complete like 90% of what is involved in a building inspection with a thermal camera. This app is not liking my shortcuts. Yeah, so if you have something like this, you can just like run around your home and be like, there's a gas leak there, because you can just see like the temperature. Actually, one thing that I think is very, very cool that I was not expecting to happen is you can actually see where I've been standing on the ground. Like my footprints keep the ground warm for a while afterwards. How cool is that? Like you can like see where people have been standing. How sick is that? Yeah, suffice to say, this is a little bit of a toy, I think. But I also actually think it will be genuinely very helpful as well, to just see what things are getting hot, how hot they're getting. The guy whose video I've linked to, he did testing with this where he had like a very accurate, he was doing like testing specifically for like PCB applications to see how accurate it was. And it was within like, from memory, it was within like a degree or two at most. I think it was actually a bit less than that. But like plenty fine for hobbyist use. It's like, oh, which component is getting super hot right now? Oh, I can see very clearly that one. Done. So good. Definitely recommend. Definitely check it out. And if anyone has any suggestions for how to make my tube a bit stiffer, I would love to know. I'm considering doing the heat shrink, but I'm kind of nervous that if that doesn't, I don't know. It seems like a bit of a waste of heat shrink if it doesn't work, because it's like a whole meter long. But maybe it's worth trying. Anyway. That was another thing where I was just like, it didn't work, and I was like, fuck this. Like, I'm done with you for now. So I think it's been a couple of days now, and I feel a little bit better about it now. So I think I might return to it over the weekend or something and see if I can fix it. Yeah, I've definitely, this last couple of weeks has definitely been a good exercise in knowing when to just stop. Knowing when to say, okay, cool, I'm getting too frustrated with this. I need to just step back a bit. And being sick does not help either. My tolerance for frustration is definitely a bit lower over the last couple of days while I've been a bit sick. But we're getting there. All right, cool. I think that's everything. Yep. I did not check my calendar but I believe I have nothing on next week. So there should be a stream next week. I know I said this a couple of weeks ago and we ended up having like a 3-week hiatus, but I believe there's nothing. Yep, quick check now. Yep. Should be a stream next week. Cool. We'll see what I do. Yeah, there's a couple different avenues for me to take right now, but I just really want to get Butler to work. So that's my main motivation right now. Yeah, but we'll see how we go. Yep, cool. As always, if you have any feedback on any of this, then please let me know, because yeah, it saves me a lot of wasted time when people realize that I'm doing something stupid and I don't realize it. So that's very helpful. And yeah, as always, I hope you found this interesting, and I will see you next week. Hopefully. We'll see. Hopefully I don't get any more sick. Yeah, we'll see how we go. All right, until then, have a good one. And good luck with everything you're doing. I forgot my phrase. It's been so long. My God.